Good day. Today we are discussing about one of the important area in design of machine elements, that is theories of failure. So, what is the design process? For example, consider a circular bar subjected to load P. Okay, it's a or load P or subjected to a stress sigma 1 in x direction. Okay, it's a uniaxial condition. That means in x direction only the stress is acting. The stress acting in x direction is equal to sigma 1. So how can we design this bar? Designing means determine the shape and the size of the member. So here, to calculate the size of this member, and first we need to identify the material. So based on the material, we can draw a stress strain diagram. So based on the material, for example, if it is a mild steel or if it is an aluminum material, then we can draw this is a ductile material and this is the yield point of that material. Okay, this is the strain and this is the stress. So this is the stress strain diagram of that material. So from this we can say this points corresponding to yield point and corresponding stress is called yield stress. Okay. And here in this theories of failure, the important term is failure. What is a failure? So failure can be defined in two terms. The first one is the complete a member or a structure completely failed or completely fractured during the working condition. That is a one type of failure. So complete fracture is the one type of failure. And next there is another type of failure, that is the severe deformation. Severe deformation. That is also a type of failure. Okay, so these are the two types of failure. So when we design a member for a particular applications, so that member should resist against fracture, and at the same way the material or the member should resist against severe deformation. So minute deformation is allowable, but it should resist severe deformation. So we have to design a member based on the fracture criteria as well as based on the severe deformation criteria. Okay, so for that, for example, in this member, first draw the shear stress strain diagram for that material. So in this sigma y, we know what is yield stress. After yield stress, we know there will be a permanent deformation. Okay, so when we apply a stress which is below the yield point, then we can say when we release the stress, the material or the structure come back to its initial shape and size. So below the sigma y, any stress is capable, or the member is capable to carry up to sigma y stress. Okay, so when the stress exceeds sigma y, the member is permanently deformed. So that is one type of severe deformation. So if we consider if we are not allowing any type of deformation or permanent deformation, we have to design based on sigma y. We should design based on sigma y. Okay, so if we design based on sigma y, the member will not deform permanently. Okay, so sigma y is the design criteria against this type of failure, severe deformation. And if you want to, the deformation is allowed, and if you consider only the fracture, then this will be the design criteria, the sigma u or ultimate stress. We know after ultimate point the necking is formed and material fractured or failed. Okay, so this is the maximum stress carrying capacity of that material. So sigma u is the fracture condition. So if you want only resist to fracture, the deformation is allowed, then we can design based on sigma u. Okay, but commonly when we design any structure member, we consider both conditions. That means the structure should resist against fracture as well as severe deformation. So commonly in our structure members, we use sigma y as the design barrier or design condition. Okay, so sigma y is the design condition. And next one time we studied is factor of safety, FOS. What is factor of safety? If we design based on sigma y, then if any change in the stress applied on the member, there is a chance for crossing the sigma y. Okay, there will be a chance for crossing this sigma y. There are different uncertainty may develop on the structure member, like a earthquake or any other wind, severe wind, etc. So during that condition, there is a chance for crossing the sigma y. So we have to maintain a safety to avoid this type of crossing. Okay, for that we use factor safety. So what we do, instead of designing with respect to sigma y, we design based on sigma allowable. Sigma allowable. What is sigma allowable? Sigma allowable is equal to sigma y by factor safety. So we divide the yield stress with respect to factor safety. Factor safety always greater than 1. Greater than 1. So if you divide with a sigma y with a value which is greater than 1, so this right hand side will be always less than sigma y. Okay, it will be always less than sigma y, or we can say sigma allowable will be somewhere in the bottom of this sigma y, maybe here. So we design based on this point. So if there is any uncertainty or uncertainty load is developed, like wind or earthquake, it may only cross this point. Okay, so it will not cross the sigma y point. So we can ensure the safety of the structure member by considering the factor safety. So for any design, we should consider the sigma allowable for the design, and that is equal to the yield stress divided by factor safety. So that is the design of a very simple member subjected to a uniaxial stress or the stress in a single direction. So here in this bar, circular bar subjected to only stress in the single direction, x direction. Okay, so how can we design this? So when this subjected to sigma 1, so we know what is the, or if we can say that is load P is acting here, P1. Load P1 is acting here. So when it is subjected to load P1, what is the stress developed across any cross section perpendicular to P1? So stress developed will be equal to sigma 1 is equal to P1 by A. P1 by A. So that is the stress developed. So what is the design condition? When we apply load P1 across any cross section of this bar, a stress will be developed, that is equal to sigma 1. And if this sigma 1 cross this sigma allowable value, then there will be a failure. Okay, if the stress developed based on this P1 value across any cross section of this bar, if it is crossed this sigma allowable value, okay, so the limiting condition is sigma allowable value. If the stress develop across any cross section of the bar cross sigma allowable value, then there will be a failure. So this is the essential condition. The sigma 1 always less than, should be less than sigma allowable, or in a equal to. Okay, so this is the condition. So we can design based on this instead of in this equation instead of sigma 1 we can use sigma allowable. So sigma allowable equal to P1 by A. So if you know P1 and the sigma allowable is the allowable stress of the material. So it is a material property. Sigma allowable is equal to sigma by factor safety. Sigma y is the material property. For a steel, there is a specific value of sigma y. For aluminum, we can say a specific value of sigma y. We can find it from the stress strain diagram of that material. So from this, we can calculate the sigma allowable. So this is a known value. This the load acting on the member is also a known value. From this, we can calculate A. From this, we can calculate the diameter. So this is the design. Okay. So in this design, we have two known value. What are they? The load acting on the member. We know the load acting on the member, and we know this sigma allowable. Sigma allowable is equal to sigma y by factor safety. Sigma, from where we got the sigma y? From the stress strain diagram, we got the sigma y value, the yield stress of the material. It is a material property. So we sigma y by factor safety. By equating these two values, we got area. From this we can calculate the diameter. So what is the importance of the diameter? So if you make a structure or a component with a diameter, for example, this is equal to 10 mm. 10 mm, then what is the stress developed in this material? The stress developed will be equal to sigma allowable. Okay, it is not cross the sigma allowable. Okay, so the stress developed across any cross section will be in this bar will be always less than or equal to sigma allowable. So we can ensure the safety of the material by satisfying these two conditions: severe deformation and fracture. So this is a simple case, a bar subjected to uniaxial tension. Okay, but this is not the case for actual structure members. In case of actual structure member, it is subjected to different types of load. Okay, the member may be subjected to torsion, it may subjected to bending, or it may subjected to different direction, tensile, compressive, load, normal stresses, etc. So different types of load may act on a structure member. So how can we design this type of member when it is subjected to this type of multi-dimensional loads? So that is based on this theories of failure. That is the importance of theories of failure. Okay, so we already studied in our first module about the stress at a particular point. So what is the stress at a particular point? For example, consider this circular bar subject to different types of loading on this. So at a particular point, how can we find this stress at this point? So we can consider a very small elemental area around this point. Okay, and from this elemental area we can calculate the different stress values. There are 6 components of stress. What are they? Sigma x, sigma y, sigma z, tau xy, tau yz, tau xz. These are the 6 components of stress. Okay, so this indicating our stress tensor indicating the stress at a particular point. Okay, similarly strain at a particular point also can be calculated based on the 6 component of strain, that is epsilon y, epsilon x, epsilon z, gamma xy, gamma yz and gamma zx. These are the 6 components of strain also. Okay, so stress and strain at a particular point can be defined using these 6 components of stress and 6 components of strain. So this is called stress tensor. Okay, and in case of 2D, this is the case of a 3-dimensional because we can see the 3-dimensional stress in normal and tangential. And in case of 2-dimensional condition, 2D condition or plane stress condition, we know this is sigma x, sigma y, and sigma is there is a sigma z value, but it is equal to 0, and tau xy. Similarly, epsilon x, epsilon y, epsilon z value is there, but it is 0, gamma xy. This is the 2-dimensional condition. Okay, we already discussed about this, and using the MOS circle also we can calculate the principal stress and stress on any inclined plane. Okay, so as I said, for a particular material, if we take any material, so if you take any material, for example, take aluminum material, we can draw the stress strain diagram. This is the aluminum stress strain diagram for aluminum, and we can say this is the yield point sigma y. and this is the ultimate point sigma ut. Okay, sigma ut, that is ultimate point. So consider a member subject to different types of loading. Okay, for example, so after conducting the tensile test, we can draw this stress strain diagram. So from this stress strain diagram, so this is my specimen. This is the stress applied axially in one direction only. Okay, so this is equal to P by A. The stress applied is equal to P by A. Okay, so here in this member, when it is subjected to this type of stress, what is the maximum principal stress? First one is maximum principal stress. Maximum principal stress. So we can draw a Mohr circle, and from this we can calculate the principal stress. Okay, so here in this is the x direction and this one is the y direction. Okay, so here in this Mohr circle, this is the shear stress direction, this is a normal stress direction, and here we can see in x direction there is no stress. So sigma x in direction is equal to 0. So this is the first x plane. Okay, and in y direction we can see a stress, that is sigma. We can say sigma y. So this is the, from the origin we got sigma y. Okay, and the shear stress here is equal to 0. So we can draw a circle passing through the 2 points. Okay, this is the Mohr circle. And from this Mohr circle, it is clear that the maximum stress will be equal to sigma y. This is the maximum normal stress, that is equal to sigma 1. But this sigma 1 equal to sigma y. So from this, when a body is subjected to uniaxial stress, the principal stress sigma 1 will be equal to sigma y. And what is the minimum stress? Sigma 2. Sigma 2 equal to 0. The minimum stress is equal to 0. So we got sigma 1 is equal to sigma y. So that is the principal stress. So based on this, actually we already discussed this. Based on this principal stress, we design this member. Okay, actually this sigma 1 is the principal stress. Okay, but unfortunately the principal stress sigma 1 is equal to this. In the case of uniaxial stress, the applied stress is equal to the principal stress. Okay, so we got the maximum principal stress. Based on the maximum principal stress, we can design this member. Okay, next, what is the maximum shear stress? Maximum shear stress. Maximum shear stress here, again from the Mohr circle, we know this is from the center. If you draw a line like this, this is the tau maximum. This is the tau maximum. So we know what is the diameter of this circle, sigma y. Okay, then what will be this value? The radius will be equal to sigma y by 2. Sigma y by 2 will be the radius. Okay, so tau maximum we can write tau maximum equal to sigma y by 2. Okay, because sigma y total diameter is sigma y, so radius will be sigma y by 2. This is also radius. Tau maximum also is radius. So it is equal to sigma y by 2. So maximum shear stress on this member. So here actually the shear stress is developed on a plane that is at an angle 45 degree with the direction of stress. Okay, this will be 45. Okay, at a 45 degree angle from the direction of loading, we got a maximum shear stress plane. And what is the value of maximum shear stress? Sigma y by 2. Okay, and next one is maximum principal strain. So what is the maximum principal strain? It's very easy. If we know the maximum principal stress, that is equal to sigma 1. We already calculated sigma 1. That is equal to sigma y. Okay, So again sigma 1 by E. Strain is equal to sigma 1 by Young's modulus. Stress by strain is equal to Young's modulus. So strain is equal to sigma 1 by E, or which is equal to sigma y by E in this case. So that is the maximum principal strain. Another one is the fourth one, that is the at the point of failure, the total strain energy density. Total strain energy density. Total strain energy density. So we know what is strain energy. That is the energy stored in a deformed material per unit volume. That is the strain energy. You already studied about the strain energy. So strain energy can be calculated using this equation sigma y square by 2. That is the strain energy equation. Okay. So half into stress into strain. From this we can calculate this sigma square by 2E. That is the strain energy. And another term which is used while developing the theories of failure is this one, distortion energy. Distortion energy density. Distortion energy density. So what is distortion energy density? In this strain energy, so when we apply some amount of load on this member, for example, in this member is loaded with the different types of load, okay, and this member is deformed like this. This member is deformed like this, okay. So for this deformation, some amount of strain energy will be developed. Okay, when we apply an external load, this member is deformed like this, and this deformed body have some strain energy. Okay, so the total strain energy is equal to volumetric strain energy plus distortion strain energy is equal to volumetric strain energy plus distortion strain energy. So what is this volumetric strain energy and the distortion strain energy? So for example, when a body is subjected to hydrostatic stress, for example, if this body is subjected to hydrostatic stress, what is hydrostatic stress? A stress acting in every direction is same. Okay, stress acting in every direction or strain in every direction will be same. Okay, so when this body is subjected to hydrostatic stress, there will be volumetric strain. That means there is no change in the shape of this body because everywhere the stress is same. So there is no stretching or contraction of this body under the application of same stress. Okay, so but there will be a volumetric change or volume change. So this type of stress is called, or this type of strain is called volumetric strain. Okay, so when this body is subjected to different types of stress, for example, sigma 1. Okay, it is subjected to sigma 1, sigma 2, sigma 3, sigma 4. Okay, so when this body is subjected to different types of stress, there will be strain also in this body, and this strain can be divided into two. Okay, this strain can be divided into two. So under the application of this stress, there will be volumetric strain plus distortion strain. Okay, so there will be volumetric strain plus distortion strain. Under volumetric strain, everywhere the volume, the shape, there is no change in the shape. Okay, under this volumetric strain, but there is a change in volume. And under this distortion, the entire shape will change. The shape is distorted, but the volumetric strain is 0. Okay, because there is no change in volume, the under the external stress, the shape will change. So this total strain energy can be divided into volumetric strain energy plus distortion strain energy. From this we can say SD, the distortion strain energy, is equal to total strain energy minus volumetric strain energy. And this is equal to total strain energy. We know the equation of total strain energy, sigma y square by 2E minus 3 into sigma m square by 2E into 1 minus 2 mu. So that is this term is corresponding to volumetric strain. So that is also you have studied while studying this bulk modulus. In the derivation of bulk modulus, we have studied this equation, the volumetric strain. Okay, where sigma m is the sigma y by 3, the mean stress. So from this we can calculate sigma y square by 2e minus 3 by 2e into sigma y by 3 whole square into 1 minus 2 mu, that is equal to sigma y square by 6g. That is the amount of distortion energy. Sigma y square by 6g, where g is the modulus of rigidity. Okay, so distortion energy is nothing but it is the amount of energy stored in a strained body and that is developed based on the distortion. Okay, that is, so out of this total strain energy, there are two parts, volumetric strain energy as well as distortion strain energy. And the volumetric strain energy is the strain energy stored in a deformed body per unit volume under volumetric strain. Volume change, under volume change, the energy stored under volume change. But this SD is the amount of strain energy stored in a distorted body when it is subjected to shape change, and that is equal to sigma y square by 6g. Okay, so here we studied 5 conditions. So when a body is subjected to uniaxial loading, there is a principal stress, there is a maximum shear stress, there is a maximum strain or principal strain, then total strain energy stored is this much, total distortion energy developed is this much. Okay, and when body is subjected to this uniaxial stress, the deformation or yielding of the body is based on, it may be based on any of this condition. Okay, the yielding of the body when subjected to external stress will be based on, it may be based on the maximum principal stress, or it may be based on maximum shear stress, and it may be based on maximum principal strain, or strain energy density, or distortion energy density. Okay, so based on this 5 conditions, we develop a theory, that is the theories of failure. That is the theories of failure. So the yielding of the material is due to, so the yielding, for example, the initial size of the member is this much. When subjected to sigma y, that is the yield stress, normal stress, sigma y, normal stress in the y direction. When subjected to normal stress, its length is increased, or it's subjected to deformation, or it's subjected to yielding. So what is the reason for this yielding? The reason is because anywhere in this body, or at any point on this body, the stress or attainment of maximum principal stress is equal to sigma y value. Okay, at any point on this body, a principal stress is developed, and when this principal stress attain the sigma y value of the material, then there will be yielding. So that is the first case. What is the second case? Again, for this body, at any point on this body, a shear stress is developed. Maximum shear stress is developed. That is equal to sigma y by this sigma y by 2. And if this maximum shear stress is attained, which is equal to the shear stress corresponding to yield point, okay, of the material, the shear stress, maximum shear stress at any point on the body reached the shear stress corresponding to the yield point of the material, then the material is, or the body yield because of the second condition. Because of this second condition. So this is another reason for the yielding or deformation. So this is the first reason, this one is the second reason. Okay, we don't know which one is the exact reason for this yielding, but these are the different cases. Okay, so the third case is maximum principal strain case. What happened when we apply sigma y at any point on this body, a strain will be developed. Maximum normal strain will be developed, and that maximum normal stress that is equal to sigma 1 by E or sigma y by E. And this maximum normal strain, if it is equal to or greater than the strain corresponding to yield point, the maximum strain corresponding to yield point of the material, then there will be a yielding on this body. So that is the third case. What is the fourth case? Fourth case is this one, when a body is subjected to this type of loading, some amount of energy is stored, strain energy is stored per unit volume, that is equal to sigma y square by 2e. And if this strain energy stored in this body is equal to or greater than the strain energy corresponding to the yield point of the material, then there will be a yielding or deformation of the material or body. So that is the fourth case. The last case is distortion energy density. Again, we derive the distortion energy, that is equal to sigma y square by 6g, and that is the distortion energy produced by on this material by the uniaxial loading. And if this distortion energy density is greater than or equal to the distortion energy corresponding to the yield point of the material, then there will be a yielding or deformation of the material. So we studied or we discussed the 5 conditions for the yielding. Okay, we don't know exact reason or exact condition for the yielding. So later we will discuss which one is the exact case for the yielding. But there are 5 reason or 5 conditions for the yielding. Okay, so based on these 5 conditions, actually we develop 5 theories of failure. So for varieties of loading, the main problem of complex loading condition, for example, consider a case of a shaft. This is subjected to torsion T. Okay, a torque is developed, and in the same shaft an axial load is applied, P. An axial load is applied. On the same shaft I am applying a bending moment. A bending moment is applied. So this shaft is subjected to 3 types of loading. So this is a variety of loading condition. Okay, so in this condition it is very difficult to calculate it is very difficult to design this component. Okay, so in the previous case it was very easy. In this case it was very easy because here we have only one lot. We can plot a stress strain diagram. From this we can calculate sigma y. From this we can easily calculate the diameter. So this is a simple uniaxial condition. So in this uniaxial condition, it is very easy to calculate these all the parameters. But in this case, it is a very complex condition. So such complex condition, we have to develop different theories to design this body. Okay. So that is actually we do in the case of theories of failure. So for designing this body, actually we do one test. So based on the material which is used to make this shaft, we do a one test. For example, if it is an aluminum bar, we do one test and we calculate the parameter sigma y, that is a yield point. And from this we collect different data, the sigma y or sigma u also we collect ultimate stress. So that is the material data we collect by conducting this uniaxial tension test. And using this material data, sigma y and sigma u, actually we try to find out the load capacity in the new situations, in such type of new situation. Okay, that is actually what we do in the theories of failure. Okay, so here in this when the sigma y and the sigma ut value in the uniaxial tension stress is known, by testing we can calculate the sigma y and the sigma u. So all the theories of failure, all the theories of failure actually relate the uniaxial tension test parameters with the complex loading condition. So this is very important. So in the complex loading conditions, actually what we do is that we design this complex loading condition based on the data from single tension test, uniaxial tension stress. So this test is conducted with the same material. We use the same material with the standard size, and in this we apply a uniaxial load and we plot this graph. Okay, so from this we got different parameters. Using this parameter we can design this complex loading condition. And for that, so we relate these two areas using theories of failure. So that is the importance of theories of failure. So here we studied, we are going to study 5 theories of failure. The first theories of failure is maximum principal stress theory. Or Rankin's theory. There are two names. So this is the first theory. According to this theory, failure will occur. So how this complex loading condition member will fail? According to this theory, this member fail when the maximum principal stress at any point, the maximum principal stress reaches the value corresponding to the yield point in the uniaxial tension test of that material. So that is the maximum principal stress theory. So here by using this theory, actually we relate these two parameters. Okay, so here if you take any plane, that is the principal plane, there will be a principal stress, for example sigma 1, and this principal stress, and if you take the material of the shaft and we plot a stress strain diagram after conducting the uniaxial tension test, we got the sigma y and sigma u, and we relate the sigma y with the sigma 1. Okay, so we calculate the sigma 1 based on the sigma y value. This is a known value. From after conducting the tension test and drawing stress strain diagram, we can calculate the sigma y value. From the sigma y value, we can calculate the sigma 1 using this theory, maximum principal stress theory. Okay, so that is the theory. So in this theory, according to this theory, failure will occur when maximum principal stress, that is the maximum principal stress, this one is the maximum principal stress, reaches the value corresponding to the yield point, this one, in the uniaxial tension test. So that is the maximum principal stress theory. Okay, so that is so in this, consider a plane stress condition. Sigma 1 is acting in x direction, sigma 2 is acting in the y direction. Okay, so here in this, for example, sigma 1 is greater than sigma 2. Sigma 1 is greater than sigma 2. So that is first condition. So here in this, we can plot a MOS cycle diagram. Okay, we can plot a MOS cycle diagram in this case. So this is the sigma, here in the sigma 1 is greater. So this one is sigma 1, this one is sigma 2. Okay, sigma 2, and shear stress value equal to 0. There is no shear stress acting on this member. So we can draw a circle passing through this sigma 1 and sigma 2. We can draw a MOS cycle. Okay, so what is the maximum principal stress? Again, this is equal to maximum principal stress is equal to sigma 1, minimum is equal to sigma 2. Okay, there is no change. This x component of stress is equal to this principal stress, and the y component stress is equal to the minimum principal stress. Okay, so here the principal stress sigma 1, that is the maximum principal stress. Okay, so if it is greater than or equal to sigma y, this is the sigma y is nothing but it is the yield stress corresponding to this point for this material. Okay, yield stress of this material. So if this maximum principal stress is greater than or equal to sigma y, then there will be a failure. So this is the condition of failure. First condition of failure. And the second condition, sigma 2 is greater than sigma 1. So in this case, sigma 2 is greater than sigma 1. Okay, so here again we can plot a MOS cycle. Here sigma 2 is greater, so this one is my sigma 2, that is the external stress acting on this body, sigma 2. Okay, and sigma 1, this one is the sigma 1, so this one is sigma 1. Again draw a MOS cycle. So here shear stress is 0. You can say shear stress is 0. So this one is the maximum principal stress. Again sigma 2 is the maximum value. Sigma 2 is the maximum value. Okay, so maximum principal stress sigma 2. So here this is the condition. Sigma 2 is greater than or equal to sigma y. Sigma y is the yield stress. So that is the second condition for the failure. Okay. Again, we can again draw the same with the sigma compression also. So here the components are under tension. If it is under compression, it will be minus sigma 2 greater than or equal to minus sigma y. Minus sigma 1 is greater than or equal to minus sigma y. This is the condition. So we can plot the variation in a a sigma 1, sigma 2 graph. Sigma 1, sigma 2 graph. Okay, so here what is a condition for the failure? This one. Sigma 1 at least should be equal to sigma y. Okay, so this is the direction sigma 1. So for example, this one is sigma y. This one is sigma y. Then we can draw a line like this. So to the left of this line, sigma 1 is less than sigma y. To the right of this line, sigma 1 is greater than sigma y. So this way to the right it is a failure zone. To the left it is a safe zone. Again, using this equation, sigma 2 at least should be equal to sigma y for the failure. So for example, this is sigma y. This one is the sigma y. So I draw a horizontal line. If the sigma y is greater than this sigma 2 value, sigma 2 is greater than sigma y value, that means that in this side, this is a failure zone, and this one to the bottom, it is a safe zone. So we can say this area is a safe region, and this area is a failure region. So the combination of sigma 1 and sigma 2 outside this rectangle will be a failure of the member under principal stress theory. Okay, and same rectangle can be plotted on this 3 coordinate, and here if the sigma 1 is negative or compressive and sigma 2 also compressive, then similar sigma y can be minus sigma y can be drawn here, and minus sigma y can be also drawn here. So this is also safe, and here again one is compressive and one is tension. We can draw rectangle like this. So all these are inside this 4 rectangle, it is a safe region. Outside the rectangle, it is a failure region under theories of failure. So these are the conditions for the theories of failure. So principal stress across any point on the body should be less than or equal to sigma y for a safe design, for a safe design. But if it is the sigma 1 is greater than the stress develop or the maximum principal stress develop across any point on the body, if it is greater than sigma y or equal to sigma y, that is the condition of failure. Okay, so if you design any body like a complex condition, everywhere, any point on this body should not develop a maximum principal stress which is greater than sigma y. If a maximum principal stress is developed across any point greater than the sigma y value, then there will be a failure. So that is the first condition. Second one is maximum shear stress theory. Or Truscott theory. According to this theory, failure will occur when maximum shear stress in the material reaches the value corresponding to the value at the yield point in the uni-axial tension test. So again, we can draw the complex loading condition. So this is another complex loading condition. The load P is acting and subjected to torsion T, subjected to bending M. So this is a complex loading condition. According to maximum shear stress theory, at any point on this body, the maximum shear stress develop. For example, on this point, a shear stress tau maximum is developed. That is the point where the tau maximum is developed. Maximum shear stress is developed. And if this maximum shear stress develop on this body under complex loading condition, will fail when this tau maximum is greater than or equal to the shear stress corresponding to yield point. Corresponding to yield point, this is the yield point of the aluminum material, and corresponding to yield point there will be a shear stress. So shear stress corresponding to yield point is less than the tau maximum, the shear stress developed on the body under this complex condition, then there will be failure. Okay, so we have to design this body for a safer condition. We have to design a body and such that at any point on this body, the shear stress, maximum shear stress developed should be less than this tau y. Then it will be safe. But if anywhere at any point the maximum shear stress developed is greater than this shear stress corresponding to the yield point of the material, then there will be failure. That is a maximum shear stress theory. So consider this element. Consider this element subjected to sigma 1, sigma 2 load in the x and y directions. Okay, and in this, what is the maximum shear stress in this loading condition? Using MOS circle, we can calculate the maximum shear stress. Here, sigma 1 is the x direction, that is the sigma 1. And in y direction, that is the normal stress sigma 2. There is no shear stress acting on this body externally. Okay, so we can draw a MOS circle. MOS circle. And in this MOS circle, this is sigma 1 and this is sigma 2. And what is the diameter of this MOS circle? That is sigma 1 minus sigma 2. Sigma 1 minus sigma 2 is the diameter of the MOS circle. This one. Then what is the radius of the MOS circle? Sigma 1 minus sigma 2 by 2. And this is the maximum shear stress, tau maximum. This maximum shear stress is equal to radius of the MOS circle. That means tau maximum equal to sigma 1 minus sigma 2 by 2. Okay, so tau maximum equal to sigma 1 minus sigma 2 by 2. If sigma 1 is greater than sigma 2. Okay, and this tau maximum is developed on this plane. We can see a plane here that is at an angle 45 degree with the sigma 1 and a sigma 2 direction. And in this plane, a normal stress is developed. Sorry, a shear stress is developed. Maximum shear stress is developed. Tau maximum is developed here. This is not normal. Sorry. Maximum shear stress is developed on this plane. That is at an angle 45 degree with the sigma 1 and a 45 degree with the sigma 2. Again, consider another case. This is a plane stress condition. And in a plane stress condition, the sigma 2 is absent. Here in this case, sigma 2 is absent. There is a sigma 1 value. But sigma 3 is in a plane stress condition. Actually, we have sigma 1 or sigma 2. But sigma 3, there is a sigma 3 value in the z direction, but its value equal to 0. So here in this body subjected to sigma 1 in x direction, and in z direction we have sigma 3 which is equal to 0. That is a plane stress condition. Okay, here also we can draw two planes subjected to maximum shear stress. This is the first plane and this one is the second plane. Both the planes are at an angle 45 degree with the sigma 1 and the sigma 3. Okay, so in this case, what is the value of tau maximum? Tau maximum is equal to sigma 1 by 2. So that is also we can draw using a MOS circle. So in this case, sigma 1 value, we have a sigma 1 only, sigma 2 equal to 0 and sigma 3 also equal to 0. So we have sigma 1, this is sigma 1. Okay, sigma 2 equal to 0, this point. So based on these 2 points, we can draw a circle and this is the tau maximum. So what is the diameter? Diameter is equal to sigma 1 So what is the radius? Sigma 1 by 2. So this is the tau maximum, sigma 1 by 2. So tau maximum is equal to sigma 1 by 2. So in this case, if sigma 2 is absent, then it is equal to sigma 1 by 2. Another case is this one. Sigma 1 is 0. There is a sigma 2 value and sigma 3 also equal to 0. Okay. And in this case, from the MOS circle again we can calculate sigma maximum is equal to sigma 2 by 2. Okay. So according to Maximus shear stress theory, the failure is going to occur when the maximum shear stress, we calculate different maximum shear stress, maximum shear stress under different condition. If tau maximum is equal to sigma 2 by 2, that is the first condition. Another condition is tau maximum is equal to sigma 1 by 2, sigma 1 by 2. Another condition is tau maximum is equal to sigma 1 minus sigma 1 minus sigma 2 by 2. So this tau maximum, any of this tau maximum, that is the maximum shear stress, reaches the corresponding to the value at the yield point in uniaxial tension test, that is the failure. Okay, so this is the tau y, that is the shear stress corresponding to, this is the tau y, that is the shear stress corresponding to yield point. So if this tau maximum, that may be equal to sigma 1 by sigma 1 minus sigma 2 by 2 or sigma 1 by 2 or sigma 2 by 2, and this tau maximum, if it is greater than or equal to tau y, that is the shear stress corresponding to yield point, then there will be a failure. That is the maximum shear stress theory. Okay, so the maximum shear stress again, what is the maximum shear stress from the uniaxial tension test? If we conduct here, actually in the uniaxial tension test, we have normal strain and normal stress. Okay, so this is the actually uniaxial tension test. But this sigma can be replaced with the shear stress. How? Again with the MOS circle. So here in the uniaxial case, we have only one stress, sigma. Okay, so here in this we have only one stress, sigma 2 equal to 0. So we can draw a circle. Okay, and this is the shear stress corresponding to this MOS circle. Okay, maximum normal stress is equal to sigma. Corresponding shear stress is equal to tau xy maximum equal to tau maximum equal to sigma by 2, because diameter sigma, maximum shear stress is radius, so diameter by 2, that is sigma by 2. From this we got tau equal to sigma equal to tau maximum into 2. Okay, so here, or we can say in case of yield point, in the yield point sigma is equal to sigma y. Corresponding to sigma y, we can write using this equation. It is equal to this is equal to 2 tau maximum. 2 into tau maximum, sigma y. Okay, so this is actually written here. Tau maximum is equal to sigma y by 2. Tau maximum equal to sigma y by 2. Okay, tau maximum equal to sigma y by 2. That is written here. Similarly, tau maximum equal to sigma 1 by 2. We got this, from this we got tau maximum equal to sigma 1 by 2. So by equating this, we got sigma 1 is equal to sigma y. So that is the first condition. Second condition is this one. if sigma 2 is greater than sigma 1, greater than 0, again we can write this tau maximum equal to sigma 2 by 2, that is equal to sigma y by 2. From this we got sigma 2 is equal to sigma y. And third one is the for compressive stress. Both are, if both sigma 1 and sigma 2 are compressive stress, then we can write it is subjected to 2 stress and both are compressive in nature. Then we can write sigma 1 is equal to minus sigma y, sigma 2 is equal to minus sigma y. And one is greater than 0 and another one is less than 0. Then we can write sigma 1 minus sigma 2 by 2 is equal to sigma y by 2. So this one sigma 1 minus sigma 2 by 2 is nothing but tau maximum. Already we calculated tau maximum. So tau maximum is equal to sigma 1 minus sigma 2 by 2. So tau maximum is equal to sigma y by 2. From this we got sigma 2 equal to sigma 1 minus sigma 1. So using these values we can plot this safe zone and failure zone. For example, if sigma 1 equal to sigma y, this point, sigma 1 equal to sigma y, we can draw a line here. This is my line. And next condition, sigma 2 is equal to sigma y. That is the failure condition. So if sigma 2 is less than sigma y, then it will be safe. If sigma 2 is greater than sigma y, it is a failure zone. So this is the corresponding line. And similarly for the negative side, this is the minus sigma y corresponding to sigma 1. This is the minus sigma y corresponding to sigma 2. We got this 2 points. And based on this equation, this is the equation of a straight line. So if you give the value of sigma 1 equal to 0, then sigma 2 equal to minus sigma y. So if sigma 1 equal to 0, then this is the point, first point. When sigma 2 equal to 0, then sigma 1 equal to sigma y. So this is my point. So using this, we can draw a straight line. Similarly, we can draw another, we can use another equation, sigma 2 greater than 0, sigma 1 less than 0. Again, from this we got this equation. And based on this equation, I can plot this line also. Okay, so inside this region, this is an external region. Inside this region, this is a safer zone. Outside the region is a failure zone. So we have to select a combination of sigma 1 and sigma 2 such that it should be within this region. Then the design will be safe. Okay, so the combination of sigma 1 and sigma 2, if it is outside this region, then it is a failure zone. The design is not capable to carry the load. So that is the second theory, maximum shear stress theory. So according to maximum shear stress theory, is nothing but consider a complex loading condition. In this body at any point, the maximum shear stress, for example, in this plane, take a plane, here this is the maximum shear stress is developed. And if this maximum shear stress is greater than the shear stress corresponding to yield point, that is a tau max, then there will be a failure. That is the maximum shear stress theory. That is about maximum shear stress theory. Third one is the maximum principal strain theory or Saint-Venant theory. Saint-Venant theory or maximum principal strain theory. So of course we know when a body is subjected to external load, there will be a strain. Okay, and what is the principal strain? That is nothing but it is the maximum strain where shear strain is equal to 0. Okay, so here how the material will fail? The material will fail when maximum principal strain reaches the critical level, and this critical level given by the strain at yield point in uniaxial tensile test. So again consider the complex loading condition body. shear stress acting, normal stress acting, bending stress acting, everything is acting. So at any point on this body, there will be a maximum strain. That is the maximum normal strain. That is the principal strain, epsilon 1. And if this epsilon 1 is equal to or greater than that of the strain corresponding to yield point. This is the strain corresponding to yield point. How we can calculate this strain corresponding to yield point? Nothing but the yield stress divided by E. That is the strain corresponding to yield point. Okay. So if the strain develop, maximum normal strain or principal strain develop at any point on this body is greater than that of the strain corresponding to the yield point on the uniaxial tension test, then there will be a failure. That is the maximum principal strain theory or Stein-Weinand theory. So the material will fail when the maximum principal strain, so this is the maximum principal strain, reaches the critical value. So what is the critical value? Critical level given by the stress strain diagram at a yield point in the uniaxial tension test. Another definition, according to this theory, failure occur at a point in a body, failure occur at a point on this body when the maximum strain at the point exceed the value of maximum strain in the yield strain in the uniaxial tension test of the material at the yield point. Okay, the definition is clear. So based on this, we can calculate the maximum or the condition for the failure. So what is the principal strain? Principal strain is equal to epsilon 1 is equal to, we already discussed this in the second module. The principal strain epsilon 1 is equal to sigma 1 by E minus mu into sigma 2 by E. If sigma 1 and sigma 2 are the major and the minor principal stress. Okay, so this one is the principal strain. And what is the condition for the failure? Condition for the failure is equal to this strain developed on this body is equal to the strain at the yield point. That is the condition of the failure. That is the strain at the yield point. And this strain at the yield point and the strain developed across any point on this bodies are same, then this is the condition. So epsilon 1 is equal to sigma y by E. We already discussed sigma y by E. So we can equate these two equations, this one and this one. So sigma 1 by E minus mu into sigma 2 by E is equal to sigma y by E. From this we got this value, sigma 2 is equal to 1 by mu into sigma 1 minus sigma y. And if sigma 2 is greater than sigma 1, then sigma 2 equal to epsilon 2 is equal to sigma y by E. Or epsilon 2 is equal to again sigma 2 by E minus mu into sigma 1 by E. That is equal to, we can equate these two equations, this one and this one. So we got sigma 2 is equal to mu into sigma 1 plus sigma y. So this is the condition of, if this is the condition where sigma 1 is greater than sigma 2, and this is the condition is sigma 2 greater than sigma 1. So the equation will vary based on the which one is sigma 2 or sigma 1 is greater. And if this both are conversion, for conversion, epsilon 1 is equal to minus sigma y by E, and corresponding principal strain is equal to, equating the principal strain, this one, and so the same value. So we can plot this safe region and failure region using this value. So again, draw a line. This is sigma 1, this is sigma 2. So using the first equation, this one, sigma 1 is equal to sigma 1 minus mu into sigma 2 is equal to sigma y. So if the sigma 1 value equal to 0, sigma 1 value equal to 0, this is the equation of a straight line. Okay, so we can draw a straight line and which is passing through the point sigma y. So y is equal to mx plus c. Okay, so based on this equation we can plot a line. This one is the line passing through sigma y, and this angle is equal to 1 by mu. This angle is equal to 1 by mu using based on this equation. Similarly, based on this equation, again I can plot next line that is also passing through sigma y. So that is epsilon 2 and this is epsilon 1. And again using these conditions, I can again plot a line which is parallel to this one. And this one. So I got this type of rhombus structure, and inside region of this rhombus, that is a safer region and outside is a failure zone. And in 3D case, this is the equation. This is the equation for the 3-dimensional stress system or tri-axial stress system. In the case of 3 dimension, we have 3 principal stress: sigma 1, sigma 2 and sigma 3. So that is the third theory. So according to this theory, how can we say, according to this theory, at any point on this body there will be a principal strain or maximum normal strain, and if this normal strain is greater than that of the strain corresponding to the yield point, then there will be a failure. Okay, so that is actually written here in case of 3D. This is the strain developed on this point. 1 by E into sigma 1 minus mu into sigma 2 plus sigma 3. That is the strain at this point. And if it is greater than or equal to strain corresponding to yield point, that is sigma y by E. Okay. Next, fourth theory, that is the maximum strain energy density theory. I already said, when a body is deformed, for example, a cubical body is selected, subjected to different types of stress in the different phase, and it is deformed like this. It is deformed like this. Its length and the shape and the size is changed. Okay, so under this deformation, when it is strained, some amount of energy is stored per unit volume, that is the strain energy. So based on the strain energy, we develop this theory, that is the maximum strain energy density theory. So according to this theory, the theory of failure is based on the amount of energy supplied to the material for failure. So we have to supply some amount of energy in the form of external force for the failure. So how much amount of energy is supplied just before the failure is the amount of strain energy supplied. Okay, so based on this strain energy, we develop this theory. So the failure of the material will occur whenever the strain energy density at most critically stressed point reaches the critical level, and that critical level corresponds to the failure point in the tensile test of the yield point. So it's nothing but, for example, again consider a complex loading condition body. This is a complex loading condition body. At any point, this is the strain energy stored. For example, S is the amount of strain energy, maximum amount of strain energy stored in this body at this point. It's not at that point, the strain energy on this body equal to S. Okay, and if the strain energy is greater than or equal to strain energy corresponding to yield point. So corresponding to yield point, there is a strain energy. We can calculate the strain energy corresponding to yield point using half into stress into strain. Okay, using that equation we can our sigma square y square by 2e. Using that equation we can calculate the strain energy corresponding to yield point. So if this sigma y, if this strain energy stored in this body under deformation is greater than or equal to this strain energy corresponding to yield point of the material, then there will be failure. So that is explained using this theory. The failure of the material will occur whenever the strain energy density at the most critically stressed point, this is the most critically stressed point, reaches the critical level. And what is the critical level? The critical level corresponding to the yield point, strain energy corresponding to yield point. Okay, so strain energy density is equal to sigma square by 2e, that is the amount of strain energy on this body per unit volume. And it is the amount of energy that a material can withstand before failure. That is the strain energy. That is equal to sigma square by 2e. So we can equate this strain energy corresponding to two component of stress. This one is the strain energy corresponding to two component of stress, 1 by 2e into sigma 1 square plus sigma 2 square minus 2 mu into sigma 1 into sigma 2. And at the time of failure, this will be equal to the strain energy corresponding to yield point. This is the strain energy corresponding to yield point. Okay, so at the time of failure, this is the condition. The strain energy developed at a critical point on the body is equal to sigma y square by 2, where sigma 1 and sigma 2 are the principal stress. And in case of three-dimensional condition, there we have three principal stress. So this is the strain energy. Again 1 by 2e is also here. 1 by 2e into equal to sigma y square by 2e. That is the strain energy corresponding to yield point. And based on this equation, I can draw a safer zone and a failure zone. So we know when sigma 2 equal to 0, in this equation, if sigma 2 equal to 0, then what is the value in this equation? Sigma 2 equal to 0, then sigma 1 equal to sigma y. Okay, so we got this point. When sigma 1 equal to 0, then sigma 2 square equal to sigma y square. So our sigma 2 equal to sigma y. We got this point. Similarly, for minus sign, we got this point and this point. And we can join this using, this is the equation of ellipse. So we can join using a elliptical shape. And inside region, this inside region on stresses sigma 1 and sigma 2 corresponding to inside region is a failure, is a safer region. But outside the region, outside the sigma 1 sigma 2 region, it is a failure zone. So that is the next theory, that is the maximum strain energy theory. And the last theory is maximum distortion energy theory, distortion energy density theory, or von Mises theory for failure. Its another name is shear strain energy theory. So I already explained, we have two components of strain energy. The total strain energy at a point can be split into two components. One is a volumetric component and other is the distortion component. Okay, and in this SV, that is the volumetric component, responsible for the change in the volume of the element. So when we supply any force, the material is strained, and in that strain, how much amount of energy is used for changing the volume, that is SV. And how out of total energy supplied on a body for deformation, how much amount of energy is used for distortion, that is SD. Okay, so some amount of energy supplied is used for volume change, and some amount of energy supplied is used for distortion. So that is the total strain energy stored in the body. So here we use only distortion component, we neglect this SV. But in case of strain energy density, in this case, maximum strain energy density theory, we consider both SV and SD, volumetric strain and distortion strain energy. But in case of this maximum distortion energy density theory, we consider only this term SD. We neglect SV. Okay, so this is a very important theory. Von Mises theory commonly we used for ductile material. Okay, for example, in case of ANSYS analysis, finite element analysis, commonly we use distribution of stress in the form of von Mises stress. Okay, so mainly for ductile material, this is one of the suitable theory for the design. So SD is the distortion energy density, is responsible component of failure of the element. Or the distortion energy density has a limit, and at failure point the distortion energy reaches the critical value, and the critical value given by the strain energy density at the yield point of the material in uniaxial tension test. So the same thing for the almost similar to the previous theories. At a when a body is subjected to such type of complex loading condition, and in this body there is a distortion energy component, distortion and strain energy component, and this distortion strain energy component stored in the body, if it is greater than, in the previous theory it is S, but it can be divided into two, volumetric and distortion component. Out of this distortion component, if it is greater than or equal to the strain energy corresponding to yield point, then there will be failure. So that is the definition. So what is the value of this distortion component? Sigma y square by 6g. So I am not going to derive this equation. What is the amount of distortion energy stored in a deformed body? That is equal to sigma y square by 6g. And in terms of principal stress, it can be right 1 by 6g into sigma 1 square minus plus sigma 2 square minus sigma 1 plus sigma 2, sigma 1 sigma 2. So for the failure, it is equal to we can equate these two equations. So this is the condition for the failure. And in case of three-dimensional case, this is the condition. Sigma, the von Mises stress is equal to root of 1 by 2 into the sigma 1, sigma 2, sigma 3 are the principal stress. So using this equation, we can calculate the amount of stress required for the failure. Okay, and this is again, we can draw the graph based on this equation. Using this equation, we can draw the graph similar to the previous case. And this is also an ellipse, and inside region is a safer region and outside is a failure zone. So that is the von Mises stress theory. And so here we studied 5 different theories. Where we use 5 different theories, we need only one theory, right? Because we can use a principal stress theory or we can use shear stress theory. We don't need such type of 5 theories. So what is the importance of deriving such 5 theories for the design of a structure member? That is based on the different conditions. So the suitability of the theory is based on the failure of theories of failure for materials. So materials is very important. If you design a member made with a ductile material, you have to use different set of theories. For brittle material, we have to use different set of theories. So this is the set of theory which is used based on the material. And maximum principal stress theory, maximum principal strain theory, and maximum strain energy density theory is used for, it is applicable or which is accurate for brittle materials like casting, glass and concrete. And again, the maximum shear stress theory and the maximum distortion energy theory is suitable for brittle materials like steel, mild steel and alloy steel, etc. Okay, so when we make a component with a ductile material, you have to design based on these two theories or criterions. And for brittle material, you have to use these three strain theories of failures. So that is the important uh, point regarding the selection of the theory for the design of a component. So when we consider the brittle failure, for example, I am taking a chalk piece. I mean, you know, a chalk piece is a brittle material. Without any deformation, it suddenly failed. So we can say that is a brittle material. But for a ductile material, you know, when we apply stress, the material first initially it shows some amount of deformation, and after some amount of deformation only it starts to fail. Okay, that is the characteristics of a ductile material. So here in case of a chalk piece, it is a brittle material. So when I apply load P, what happens? The stress is developed. The stress developed is equal to P by A. Okay, that is a normal stress and principal stress also. We have already discussed based on the using MOS cycle. We can say this stress P by A is equal to the principal stress also. So according to principal stress, we can say when this principal stress sigma across any cross section reach the sigma y value or the yield stress of the chalk material, then the material failed by maximum principal stress theory. Okay, and another one is so actually when we take a chalk piece and when we apply normal stress, the failure will be like this. That means the failure junction will be a planar region. But take the same chalk piece and apply a torsion force. Okay, apply torque or twisting moment. Then the failure will be like this. Failure will be like this. Okay, a 45-degree angle or a helical manner failure when it is subjected to a torsion. You can experiment that. Okay, so what is the reason for these two types of failure? In case of a normal stress is applied, the cross section will subjected to principal stress, no shear stress. It is subjected to principal stress. And based on this principal stress theory, it failed like this. But when we apply a torsion, what happened? When we apply a torsion, consider a small element at the surface, and this is the enlarged view of that small element. Here when we apply a torsion, using this equation we can say T by J is equal to tau by R. We can say tau equal to TR by J. So there is a shear stress developed. Corresponding to torque applied, there will be a shear stress developed across the element. And this is the enlarged view of this element, and on the four faces we can see shear stress. Okay, and so this is only a pure shear condition. There is no normal stress developed on this face of the element. So we can draw a MOS circle based on this. So in this normal stress sigma 1 and sigma 2 are 0. So the first case in the x plane, that is in the x direction. So x plane we have, this is the x plane. In the x plane we have only shear stress. So that is the shear stress value. In y direction we have shear stress and x direction we have normal stress. But in the x plane we have only shear stress. So this is the point of shear stress. And in the y plane, that means in this plane, here also we have only shear stress. No, there is no normal stress. So in the y plane, shear stress is there, but normal stress is equal to 0. So we got 2 points. By joining these 2 points, we got a MOS cycle. And in this MOS cycle, we can see sigma 1, that is the principal stress, and sigma 2, that is minimum principal stress. Okay, and what is the direction of this principal stress? That is at an angle 90 degree from x plane. That means in the actual picture 90 divided by 2, 45. So this is the diagonal where this maximum normal stress sigma 1 is acting, and we know from this direction, this radius and this radius are same, or sigma 1 is equal to tau shear stress. So we got this direction, we have sigma 1 is equal to tau, and again in this direction sigma 2, in this direction we have sigma 2 is equal to minus tau. So in this chalk piece, in case of this chalk piece, how this chalk piece is failed? The failure occur sigma 1 and sigma 2 exceed the critical stress, yield stress of the failure or failure stress. Okay, so when this board is subjected to twisting moment, and some normal stress will be developed in these two diagonal direction. And if this normal stress is greater than the critical stress corresponding to the yield point of the material, then it leads to the failure. Okay, so when a brittle material like chalk piece subjected to axial load or the twisting load, both is failed by maximum principal stress theory. Okay, actually, but here shear stress is developed, but this normal stress across this diagonal is actually the reason for that. This is the principal stress. Okay, this one is the principal stress. So this principal stress is the reason for the failure of this chalk at an angle 45 degree. Then what is for ductile material? We already conducted an experiment in UTM, and after the failure we can see a cup and cone shape of a ductile material. It can be a mild steel or aluminum, any ductile material. So in this cup and cone we can see this angle is 45 with the vertical, and this cone also, this angle is 45. And this is the enlarged view. Here we can see this at the tip points, we can see 45 degree angle failure. The cup and cone arrangement after failure. Okay, so here actually what happened for a ductile material, this is the MOS circle. We have only one, in case of uniaxial tension test we have only one sigma. So this is my sigma, and corresponding normal shear stress is equal to this one, tau maximum. So if the sigma is acting in y direction, there is a normal stress in the diagonal direction, that is at an angle 45 with the loading axis. So that is this reason for this 45 degree angle failure for ductile material. And here the reason for the failure is maximum shear stress, tau maximum develop at an angle 45 degree plane reaches the critical value leading to the failure. So here in this case, for a ductile material, the shear stress develop is the reason for the failure. But for a brittle material, the normal stress or principal stress is the reason for the failure. So next we can do one example problem. So here this is a two-plate riveted joint, and in this riveted joint a vertical load of Py is acting, that is equal to 10 kilonewton, and a horizontal load of 5 kilonewton is acting in the x direction. And here in this question is to calculate the rivet diameter. What is the diameter required for the rivet? Okay, so we can calculate the diameter of rivet using the four theories of failure. Okay, here we use factor safety 3, and for the material of the rivet we take material with 270 megapascal yield stress. So this can be calculated from the stress strain diagram, and mu is equal to 0.3 and factor safety is equal to 3. So initially is given 270 is the design stress or yield stress. So using this we can calculate the allowable stress. Allowable stress is equal to design stress by factor of safety, that is equal to 90 megapascal, 270 by 3, 90 megapascal. The first case is this one. So this is the cross section of this rivet. This is my rivet, and in this rivet I take a portion. Here. Sigma y is acting, sigma x is acting here, and if you take any cross section, there will be a shear stress and a normal stress across the cross section. So if you take a small element, planar element from this cross section, this is the element, sigma y is acting in the normal direction and shear stress is acting in the tangential direction. So this is my figure. And from this we can say sigma y. What is the value of sigma y? Sigma y is equal to 10 Newton is acting actually in vertical direction. So 10 divided by area. This is the area where shear normal stress is restricting. Resistance of a area. So sigma y is equal to py by a, cross section area. And what is the shear stress? Tau xy. Here the shear stress is tangential to this plane. Okay, and that is equal to px. The tangential means this direction, the px is acting. Both are same direction. So px divided by cross section area is again the tangential load area, that is equal to a. So this is 5 kilonewton by a. That is px by a. We know that what is principal stress, sigma x plus sigma y by 2 plus or minus, plus for major principal stress minus for minor principal stress, into sigma x minus sigma y by 2 whole square plus tau x by square. And here in this case sigma y equal to 0. So sigma x equal to 0. Okay, sigma x equal to 0, only we have sigma y, that is in this direction. So sigma y by 2 plus root of sigma y by 2 whole square plus tau x by square. From this we got 12.05 divided by a. We know different values. Sigma allowable is known, mu value is known. From this we can calculate 12.05 by a. Again, sigma 2, the minor principal stress is equal to sigma x plus sigma y by 2 minus this value. So from this again we can calculate minus 2.05 by a. So tau maximum is equal to sigma 1 minus sigma 2 by 2, that is equal to 7.05 by a. So based on the first theory, tau allowable is equal to sigma 1. So tau allowable we already calculate 12.05 by a. Sigma 1, that is equal to sigma y, we know sigma y equal to 270 by factor of safety, which is 90 megapascal. So sigma allowable is equal to 90 into 10 raised to minus 3. From this we can calculate 30. Using Maximus shear stress theory, tau maximum is equal to tau allowable by 2. Substitute tau maximum is equal to 7.05 by a, tau allowable by 2. From this we can calculate the d value. Similarly, maximum strain energy density, using this, again this is the equation, using this we can calculate d is equal to 13.4. Maximum distortion energy theory, based on this, again we can calculate d is equal to 13.6. So we got different values for the d of this rivet diameter: 13.6, 13.4, 14.1 and 30. So in this, select the dimension of or diameter with a higher value, 14.1. So that is the design dimension of the rivet. So similar problem can be expert in your final examination. So concluding, statement. If you want to design any particular member, and first choose the material and check whether the material is ductile or brittle, and if it is a ductile material, use any of the theory, any of these two theory. It is a ductile material. If it is a brittle material, use any of this theory. So commonly we use maximum strain distortion energy density theory or MOS stress theory for calculation of ductile material, especially in your analysis and analysis software. So in this theory, the general statement is nothing but, in all the theories, actually what we do is that for a member subjected to complex loading condition, we calculate either maximum principal stress or maximum principal strain or maximum shear stress or maximum strain energy or maximum strain distortion energy, etc. And all these parameters is related to the value of the yield stress in the uniaxial tension test. So we cannot do different tests for finding all this value. So for the design, we only calculate the sigma y value and all other parameter value corresponding to yield stress, and then we relate these values at yield stress with the different values on different theory. For example, in case of principal stress theory, we use principal stress as a parameter. In case of principal strain theory, we use principal strain. In case of strain energy theory, we calculate the strain energy per volume. For maximum shear stress theory, we calculate the maximum shear stress at a point. And maximum distortion energy theory, we calculate the maximum distortion energy. And all these values are equated with the value corresponding to yield point, and from this we can design any component. So that is about the theories of failure. So you have to do different problems. I will give the different problems in the textbook, so try to practice this. Thank you. If you have any doubts, please ask in the next live class.